So we're looking at the second part of section 1.4, and we're going to be looking at how do limits and continuity relate, because there is a good relationship there, and it's helpful if we know that relationship, because then we can find our limits more easily. So the first question is asking us, when does a function have a vertical asymptote? Does anybody know? Okay, so when we get a vertical asymptote, this is going to be when a factor in denominator equals 0 and does not cancel with the numerator. So when a factor in the denominator equals 0 and does not cancel with the numerator. So in our warm-ups, we had this function, g of x equals 1 over x minus 3. That's the perfect example of when we get a vertical asymptote. This factor equals 0 when x is 3, and then it does not cancel with the numerator, so therefore at x equals 3, we're going to have a vertical asymptote. What type of continuity is found at a vertical asymptote? We have three types of continuity, guys. We can have continuous, which is C. We can have a removable discontinuity. Which is RD. Or we can have a non-removable discontinuity, which is NRD. So we're going to use those abbreviations, okay? So what about at this vertical asymptote? Is it continuous there? Can I, if I have a vertical asymptote like we did over here, here's the way it looked. Could I draw that without lifting my pen? No, so it's not continuous. Removable discontinuity means all I have to do is fill in a dot. Can I fill in a dot and make that continuous? No. So then what type of continuity does it have to be? Non-removable. So this is a non-removable discontinuity. If we have a non-removable discontinuity, that's also going to mean that the limit does not exist. Anytime we have a non-removable discontinuity, the limit does not exist. When does a function have a hole in the graph? Right? That's the type of continuity, but when specifically does it occur as far as the factors go? Good.
Please excuse the interruption.
So when,
at this time, would the seniors come down for picture retakes? Seniors come down for picture retakes.
So when a factor in the denominator equals 0 and does cancel with the numerator. So we have a factor in the denominator that can equal 0, but it also does cancel with the numerator. That's like our warm-up problem that was like this. Y equals 2x over times x minus 3 over x minus 3. Those canceled. Remember what it looked like? It was just the line y equals 2x. But there is a hole in the graph right there at 3, 6. So the 3 canceled, but there's still a hole in the graph there at whatever we get when we plug 3 in. So 2 times 3 is 6, so at 3, 6. So what type of continuity do we have there? Well, all I have to do is fill in this dot and it's continuous. So we call that a removable discontinuity, an RD, because I can remove the discontinuity just by filling in the dot. On these kind of functions, the limit, as we approach the removable discontinuity from the left of the function, is going to equal the limit as x approaches the removable discontinuity from the right of the function, which is going to equal the general limit as x approaches the removable discontinuity. Let me say that again. So the limit as we approach that removable discontinuity from the left is always going to be the same thing as the limit as we approach that removable discontinuity from the right, and it's always going to be the same thing as that general limit. Also remember, on non-removable discontinuities, this is when we get a constant over 0 when we try to plug in. And on removable discontinuities, this is when we get 0 over 0 when we plug in. So when we get a constant over 0, that means the limit does not exist. It's a non-removable discontinuity. But if I get 0 over 0, that means it's a removable discontinuity. There are limits, and we have to find it by doing more work. Okay, questions? All right, so without graphing, discuss the continuity for numbers 1 through 4. Use continuous, removable, or non-removable discontinuity. Okay, so on this one, we try to factor, because the factoring is the most important part. Are there numbers that multiply to be 3 and add to be 2? No, there aren't. So this cannot be factored. So what do we know then about this function then? It must be continuous. Must be continuous. I just want to show you that it is continuous. Just looking at it real quick. X plus 3 divided by x squared plus 2x plus 3. If I graph it, here's the way it looks. See how it's continuous? I can trace right over top of it and never have to lift my pen. That's what it means to be continuous. All right, let's look at the next one. We try to factor. Are there numbers that multiply to be 3 and subtract to be 2? What numbers multiply to be 3? 3 and 1 would multiply to be 3 and they subtract to be 2. So how does it factor? Good. Okay, so here's how it factors. Now I check, does it cancel with the numerator? No, so what do we have to have then? Is it continuous, removable, or non-removable? Look at what it, to be continuous, there can't be anything that equals 0 in the denominator. So when the factor in the denominator equals 0 and does cancel, well, it does, these don't cancel. So it's going to be, it does not cancel with the numerator. So therefore it's going to be what? Non-removable. So we're going to have a non-removable discontinuity at x equals 3 and at x equals -1. Just watch what this looks like. So what does this non-removable discontinuity look like? Well, here it is. Can you see how as I approach -1, see how I have to lift my pen to continue graphing? So that's a non-removable discontinuity. Then I can keep going, but then I have to lift my pen again to finish at x equals 3. So those are called non-removable discontinuities. What else are they? Vertical asymptotes, right. Will there be limits there? At x, no, there are no limits. The limits do not exist right there. All right, let's look at this one. This is one you're supposed to just know what it looks like. Do you remember this one? It's the 2 levels. Looks like this. It says without graphing, but just to remind you. What makes this equal 0 would be -4. Here's how it looks. So it always goes along, it's -1, and then it jumps up to +1. It's those 2 different levels there. So I have an open dot, but if I fill in that dot, is it now continuous? No. So what is this going to be? Non-removable. So this is going to be a non-removable discontinuity at x equals -4. So is there going to be a limit at -4 as x approaches -4? No. But there is a limit from the left and there is a limit from the right. What about this one? How can I quickly see if this is continuous? What do? Plug in 2. Good. I plug in 2 to my top part of my function, and I get 5. I plug in 2 to the bottom part of my function, and I get 3. So is it going to be continuous? No. It's going to be a non-removable discontinuity at x equals 2. And now I could quickly graph it. I don't have to graph it, but I'm just going to show you what this graph looks like. I know that I'm going to go up to 2, 5 with a line with a slope of 1. And then I have a parabola starting at 2, 3. So there's how it's going to look. I can quickly graph that. All right, so now they're going to ask us about some limits. The limit is x approaches 4 from the negative side on this function. As limit as x approaches negative 4 from the negative side. Well, I just graphed it up here. So as I approach negative 4 from the negative side, what's the y value I'm approaching? Negative 1. Would there be a general limit? If it didn't have that negative out there, would there be a general limit? No, I would say does not exist for that. But I have to have an answer for a one-sided limit. Okay, what about this one? The limit is x approaches 2 now from the negative side. Well, we went ahead and graphed this, didn't we? So the limit is x approaches 2 from the negative side is just what? 5. But graphing is like the least sophisticated way to do limits. So even if I didn't give you the picture, would you understand that you could just plug it into the top function? Since we're approaching 2 from the negative side, we plug it into the less than side. You see what I mean? It's going to be 5, no matter how you look at it. The limit is x approaches negative 4 from the positive side. Oops, I went out of order. I'm supposed to do this next. What is this going to be, guys? The limit is x approaches 4 from the positive side. What is it? 1. But what if I had asked you for the limit is x approaches negative 4 of that function? What would you say the answer is? Does not exist. I didn't ask us for that, but. All right, then for this one, as we approach 2 from the positive side, well, this is the greater than side. That means the same as the positive side, so I can just plug it in. 2 squared is 4, minus 1 is 3. Or I could look at the graph. All right, let's go down here. For the following functions, answer whether they, and let's put the word can in here. Answer whether they can occur for continuous functions, C, at C, those with removable discontinuities, meaning RDs at C, or for those with non-removable discontinuities, NRDs at C. All right, so f of C does not exist. Can that happen with a continuous function that we have no y value? No, we have to have a y value. What about at a removable discontinuity? Can that happen? Yeah, it can. Because for a removable discontinuity, it could look like this one from our warm-ups. And remember, yeah, we can just fill it in. So therefore, it can happen there for removable discontinuities. And then what about for non-removables? Can it happen there? Yeah, in fact, it does. What about the limit does not exist? What do we say for that? When's that only going to happen? Non-removables only. What about the limit from the left equals the limit from the right and equals the general limit? Removable and what else? Continuous, great. What about f of c does exist? Where can that happen? Continuous for sure. What else? Removable, it could happen too, because I could have this open dot here, but then a closed dot down here. It could look like that. So here's f of c does exist. Can that happen for non-removable discontinuities? A lot of people say no on that, but look at this one right here. This is a non-removable discontinuity. Do I have a y value there? Yes, we do. So that can happen for non-removables as well. All right, I want to give you a minute now to think about 5, 6, 7, and 8 on your own. Take just a minute, see if you can get 4 for 4 on those. All right, Kyler, what do you think for the first one? Non-removable? I disagree on that because on non-removables, the limit from the left and the limit from the right are always going to be something different. Okay, so there's only one of these where this could happen. Removable, yeah. And here's why. Because if you look at this right here, the limit from the left equals the limit from the right, but our specific y value is down there, which is something different. And that's what this is saying. This is y. So it's saying the limit from the left, the limit from the right are the same, but the y value is different. So that can only happen with removables. What's the only one where the limit from the left and the limit from the right are not equal? Non-removables. And then the limit does exist. Where's that going to happen? Continuous and removables. It can happen, and it always does happen, actually. All right, the limit exists, but it's not equal to the y value. Only one on this going to happen. Removable. And that's really the same thing as number 5. Okay, let's look at the back now. Write a function which would meet the following requirements. We have a removable discontinuity at x equals 4. Can you think of how that would look? Y equals, there's a real basic one we could use. What is it going to be? Good, Megan. So she's saying we could do x times x minus 4 over x minus 4. That's going to be a removable discontinuity because it's just going to be a hole in the graph at 4, right there. Would we have to even have the x there? You could even not have the x there, and it would still work. You could just put x minus 4 over x minus 4. That would be weird, but then it would just be the line y equals 1. It would look like that, but it would have a hole in the graph at 4, so you could do that. Okay, what about a non-removable at x equals 4? What would that be? Y equals, sure, or 10 over x minus 4, or x over x minus 4, as long as it doesn't cancel. And then a non-removable at x equals -1, and a removable at x equals 1. How's that going to look?
X minus 1 over x minus 1 and x plus 1 squared.
Okay, I like that, yeah. She's saying we could do this or this, because on this one, these would be removable, so there'd be a hole in the graph at x equals 1, right? But there'd be non-removable at -1. So we'd have a vertical asymptote at -1. All right, very good, guys. Let's look at this worksheet. I'm just going to I'll do the first row with you, just to get you started. So we're trying to find the limit, if it exists, without graphing. If it does not exist, explain why with regards to continuity. What's it always going to be if that limit does not exist? Non-removable discontinuity. You'll just put NRD. Remember that only one-sided limits may have answers of infinity or negative infinity. All right, what's our first thing we would always try to do in any problem? Just plug it in. So 2 times 3 is 6, minus 1 is 5. 3 times 3 is 9, plus 2 is 11. There's our answer. We're done. Doesn't matter if it's a one-sided limit. It's going to have the same answer as that general limit. Plugging in 1 here. 1 minus 1 is 0. 1 squared minus 1 is 0. Do we have a limit on this one? Yes, we do, because we got 0 over 0. So we have to do more work. What's the more work we're going to do? Factor, cancel, and now substitute in the number. 1 plus 1 is 2, so we're going to have 1/2. Remember, we're not plugging in -1, guys. We're plugging in 1, but it's just asking from the negative side. But if we know the answer as we approach 1, then we know the answer as x approaches 1 from the negative side. All right, let's do another one. Plug in 2. What do you get? What's the answer? 1. All right, let's do this. Not this one. I want to do one more. I want one where it's going to be infinity or negative infinity. Maybe, nope, that's not going to be it. Let's try, this one might be one. Okay, so first I try to plug in -2. -2 squared is 4, times 2 is 8. So I'd have 8 minus 6 minus 2. That's 0 over -4. Okay, this is one I want then. Because if I get 0 over -4, I know here that the limit does not exist. The general limit doesn't, but there's going to be a one-sided limit. Okay, so here's what I'm going to do. I'm going to try to factor that numerator and see if I can. I'm not sure if it can be done, but we'll try. So we're going to have 2x and x. I know a 2 and a 2 will never go in the same one, so I'm going to put a 2 here. This would be 4. And, okay, so there we go. All right, nothing's going to cancel, though. And I knew that it wouldn't. Because I got 0 over -4, oh, my goodness. What's this answer just going to be then? I was thinking we had -4 over 0, but we have 0 over -4, so the answer is just 0. See, -2 isn't causing, that's not where the vertical asymptote is. You see what I mean? Because we got 0 on the top. 0 divided by anything is just 0. I don't know, we may not have anywhere we have infinity or negative infinity. That's what I was looking for, but okay. So you guys are going to finish this up. So first try plugging in, and don't make that mistake that I just made. If you get 0 divided by something, that answer is 0. You don't need to do any more work like I did. Okay? All right, questions? All right.